Oh, hi, I'm David. Welcome to part 3 of the Topology video series. Okay, today I'm going to talk a little bit about the problem from last week, the bridges of Konigsberg, and then I'll talk a little bit about networks, introduce a new word there for you, networks, and finally give you the solution to the 9-dot problem. Okay, so first of all, the bridges problem. Last week you found out that there was this town that had an island and another island and then the land surrounding it and the Prager River. Konigsberg was the name of the city in the old Prussian Empire, and in the early 1700s the people would walk around the town seeing if they could cross every bridge at least once and not going over a bridge twice, not jumping in the water and wading or swimming across or anything like that, but just simply walk across the bridges each once. And they tried and people would not figure out how to do it, and no one could find a way, and they began to wonder, is it impossible? And you know, how do you say something's impossible? Because no one's done it doesn't mean it was impossible. Until 1969, when I was in 8th grade, no one had ever gone to the moon in thousands of years, but it wasn't impossible. So there's a difference between no one's ever done it and it's very hard and it's technically impossible. Okay, how do you prove something is impossible? And so they had to put this Konigsberg Bridge problem to rest by either figuring out a way to do it or showing that it couldn't be done, period, because it was just kind of hanging there as an unsolved problem. A man named Leonhard Euler figured out how to do this, solve this problem. I won't tell you whether he solved it by finding a path or whether he proved it impossible. I'll just say he solved it, he put it to rest, okay? And what Euler did was he developed a theory called network theory. Networks are like points with lines connecting them or paths connecting them. Okay, each point is a vertex, so the points are called vertices. Notice that the plurtex. Okay, this is good. The plural of vertex is not vertexes, it's vertices. Okay, so we have vertices and paths connecting the vertices, making networks. I'm going to show you some examples of networks, and then when we talk about networks, the challenge is, can you trace the network without lifting your pencil or going back over a path more than once? You can go through the dots more than once, but you can't go back over a path more than once. So they say, is a network traceable or not? And I'm going to leave you with some network problems to try on your own and see if you can trace them or not. And as we trace the network problems, what you want to ask yourself are 3 questions, okay? First of all, can it be traced? And then second of all, if it can be traced, can you start anywhere you want, or do you have to find certain points where you might start? And thirdly, you ask yourself, maybe is it impossible to trace? Okay, so we'll classify the networks as easy to trace, start anywhere. More difficult to trace, you have to find a certain starting point and ending point, or impossible. Can you trace the snowman figure without lifting your pencil and without going over any line more than once? So let's try this snowman little problem, this network. Here's something you might try to make this easier to work with. Take a sheet of paper and draw the little network. In this case, the snowman, and it looks basically like this. And if you say, well, that's not a network, it's a network. Think of the places where the lines meet as being the vertices. So we have the vertices and we have the paths. And if you'd really like vertices, you could add another vertex here or here, wherever, and it doesn't change the problem any, but this is your basic network problem. Now, when you want to trace it, take a piece of wax paper and just put it over the top, okay? Now let's try to trace the figure and see what happens here. Maybe I can start here. I'm going to trace it in red, okay? I'll go to here, maybe around. Okay, let's see. Maybe I can come around here even. Let's try this and see what happens, okay? And now I'm thinking, do I want to go this way or this way? It looks like I'm kind of stuck because now I'm at a point where I have nowhere else to go, and you can see that this did not get traced. But see, the thing with the wax paper is just slide it over, and let's see, maybe I can start here. So I'm going to cover this whole thing, okay? This whole thing. Maybe I'll go down, okay? Wow, I think I'm going to be able to get this one, but guess what? Oh man, didn't work. So you got to keep trying this, okay? Keep trying the networks. And when you do your other networks, do the same thing. Get some wax paper out and try drawing them on the paper, and then, you know, tracing them on the wax paper so you don't have to keep on redrawing the figure over and over again. Okay, so good luck. Which figures can be traced without lifting your pencil? Which are easy, where you can start at any point? Which are hard, you have to find the right place to start? And which are impossible? I will put this picture up at the end of the video so that you'll have a chance to copy these. In this 9-dot problem, we have the 9 dots arranged in a 3x3 array, and we have to connect all the dots with 4 lines. Now, you do not have to stay inside of the square that you see there. That's a self-imposed restriction, and that's what keeps people from solving it. So if you're willing to go outside of the square to solve it, then it's solved rather quickly. Now the solution to the 9-dot puzzle. Okay, we're going to use the problem as given. We'll draw the first line, then the second line, and now the third line, and the fourth line, and it is done. Wow. Thank you for watching this video. If you liked it, please feel free to share with friends, subscribe to my network, and always hit that little like button. Okay, so I want you to just remember this. Whether you're solving the 9-dot puzzle or participating in any other creative activity, it's always good to think outside the box. Okay, thank you very much.